The last component from today's lecture will cover half-life. So half-life, and we're only going to focus on the half-life for a first-order process. Half-life is the time required for the concentration of a reagent in a reaction to be cut in half. And the equation for half-life is T1/2, that's my half-life, equals 0.693 over K, over my rate constant. So as you can see, there is no concentration in this equation. So that means that there is no relationship between concentration and half-life for a first-order reaction. For a first-order reaction, half-life is independent of concentration. So here's my initial concentration, right? 150. At what point do I reach half of that? 75. That's my half-life. So maybe about 12,000 or 13,000 seconds is my half-life. All right, going from 75 to 37.5, that's another half-life, right? So that should be the same amount of time. So if this first half-life was approximately 13,000 seconds, right, this next half-life should be a total of 26,000 seconds, but the second half-life would be, again, 13,000 seconds of time between the second half-life and the first half-life. So here's a sample calculation of half-life. If you've ever had a CAT scan done, any medical imaging, often you're given a contrast reagent to help increase the signal-to-noise ratio and improve the contrast in that imaging. So technetium-99 is a commonly used in medical imaging. It's used to enhance basically any imaging of the heart and the brain, and it relies on the radioactive technetium isotope, which breaks down in a first-order process. And the rate constant for that is 1.95 times 10 to the minus 3 inverse minutes. So what is the half-life for this process, right? So T1/2, that's my half-life, that's what I'm looking for, equals 0.693 over K. So T1/2 equals 0.693, and my value of K is 1.925 times 10 to the minus 3 inverse minutes in this case. So that means I'll get a half-life in terms of minutes. This gives me a half-life of approximately 360 minutes, about 6 hours. And this makes sense because, right, for medical imaging, you want to have a decent amount of half-life for this component so that you can administer it, it can spread throughout your body, you have time to do the imaging before this breaks down completely. And just to get an idea, right, this material has to be made. So once it's made, it starts breaking down. So you need to make it, you need to get it to the hospital, you need to administer it to the patient, and have time to do the imaging. So you want to have enough time for you to be able to make the material, get it to the patient in time, and do the imaging. So a half-life of approximately 6 hours is a decent amount of half-life. And so what does that mean approximately, right? So if I started with 100% of that material, after 6 hours, 50% of it would be left, it would be active. After another 6 hours, I would have 25% of that material left. After another 6 hours, or 18 hours total at this rate, I would have 12.5% of that material left, right? And you'd imagine the next half-life, I would go from 12.5%. After another 6 hours, I would have about 6.25%. and on again. But as you can see, that gives you a window of time to make the material, administer the material, collect the data from the test before the material breaks down completely. This is important because, as I was talking about with respect to the Chernobyl nuclear disaster, similarly with the Fukushima reactor meltdown in March of 2011, they released 28 kilograms of cesium-137. Cesium-137 has a half-life of 30 years, right? So what does that mean? That means in about my lifetime, right, what I have left, I might live through 2 more half-lives of this material. So if in 2011 we released 28 kilograms and the half-life is 30 years, that means in about 2041 we'd have 14 kilograms remaining, and in 2071, and I might be lucky enough to live that long, I'd have about 7 kilograms left. Now let's go out, right? Here's 30 years, here's another 30 years, here's another 30 years. So maybe in your life, maybe they'll figure out advanced medicine enough that you'll make it to the third half-life of this when we only have about 3.5 kilograms of this material left in 2101. But just something to think about, right? Because that material, when it was released, it was spread through the Pacific Ocean, and it's going to be with us for a while. It's going to break down with a half-life of about 30 years, which means, right, at 2041, we'll still have 14 kilograms of that radioactive material actively circulating. The important things from today's lecture, you definitely need to be able to identify a first order and a second order process graphically, right? So if it's natural log of concentration versus time, that's a first order reaction. And know the associated integrated rate law for a first order reaction. For a second order reaction, you want 1 over concentration versus time, and similarly you should know the equation, the integrated rate law for a second order reaction. So differentiate a first and second order reaction type graphically, do those calculations, be able to calculate concentration or rate constant for both a first order, second order reaction, and we're only going to evaluate half-life for first order reactions. In the next lecture, we're going to look at reaction mechanisms and catalysis.